Using ConCrete, you can calculate continuous concrete beams and slabs bearing in one direction, subjected to simple bending. ConCrete performs an organic design according to Eurocode using the limit state method. Let's illustrate the ConCrete workflow by means of a first example of a beam. The beam has two spans of 4 and 2 meters. Apart from the self-weight, there are two additional loads acting. A dead load of 20 kN per meter, including a concentrated force of 100 kN at 1.5 meter, and a live load of 10 kN per meter with a concentrated force of 20 kN. The cross-section is 250 by 500 mm. I create a new file in ConCrete. The first dialog window allows you to enter the main project data in the corresponding tab pages. Okay. Now we can enter the beam. ConCrete has a unique and interactive question-answer system for entering the model geometry, the cross-sections and the loads. Through the input panel, ConCrete asks the user for the data, which can be a name or a value. Filling out the requested data plus enter immediately raises the next question. The questions always appear in the same order. Regular ConCrete users know that order by heart and can enter, as it were, blindfolded, beams within 20 to 30 seconds. Your productivity is therefore particularly high with a tool like ConCrete. Let's start at the very beginning. Code beam is the name with which you can uniquely identify the beam on plan, and I call this B1. And I hit enter. The number of spans is 2. The width is 250. The height is 500. The number of load types, according to ConCrete, this is additional to the self-weight. In our case, we have dead loads and live loads, so 2. The length of the first span is 4 meters. The next question is regarding the number of zones. What is meant by zone? In ConCrete, geometry and loads are assumed to be constant per zone. The concentrated force is a change in loads and requires a new zone. Therefore, the first span needs to have 2 zones. The distributed load is 20. The first zone ends at 1.5 meters. That is the location of the concentrated force, and the value of this force is 100. The length of the second span is 2 meters. The number of zones is 1. The value of the live load is 10. The concentrated force is 20. I'm almost to the last question. Meanwhile, we have seen the model built up by ConCrete. When I click enter to the last question, all required data is entered. ConCrete will automatically generate the load combinations and execute the analysis. Immediately, some results appear on screen, such as the ultimate limit state, reaction forces at the supports. Using the result settings, you can opt to see additional results on screen, such as the absolute and relative deflections for the different zones, or hide already displayed results. If the height of the beam is smaller than the optimal height, ConCrete will show a minimal and optimal height, allowing you to pursue an optimal design from the start. I move on to the diagrams, and we will discuss some calculation results. At the top, there is a representation of the geometry and the loads. Next, we have the shear and the moment diagrams, deflection elastic, cracked, and after creep, and the reinforcement diagram. We can get a detailed view. You simply double-click a diagram and you can walk through different zones using the arrows left and right. Clicking somewhere or entering a value over here immediately shows the results at a specific location. Using the diagram settings, you can show or hide diagrams of your choice. ConCrete schematizes the reinforcement in a clear reinforcement sketch. For each span, you get an overview of the upper and the lower reinforcement and the stirrup zones. And that's basically the design of the first beam. Analogously, I define a second beam in real time, of course, with three spans of 5.4, 2, and 3.9 meter, a dead load of 12 kilonewton per meter, and a live load of 4 kilonewton per meter. The width is 140 and the height 390 millimeter. This beam 2 is designed, and this in about 25 seconds. All entered data can be easily modified at any time. You simply click on a parameter and enter a new value. For example, I click on the length of the second span and change it to 2.5 meter. Instantly, ConCrete automatically updates all related analysis results. Let's also go over some settings for this second beam. In the middle area, there are two palettes with icons. One palette allows you to define the calculation parameters, such as the reinforcement and the ConCrete settings, the load groups and the moment redistribution. The other palette gives us access to additional user input, such as spring supports, variable cross-sections, non-uniform loads, and moment loads. We take a look at the reinforcement parameters. These are okay. Next, the ConCrete settings. Well, assume that this beam has a ConCrete grade of 30-37. So I set the compressive strength to 30. And I update all parameters depending on this compressive strength. And okay. I choose to only adapt the active beam. The supports, they are okay. Moving on to the moment redistribution. I allow a redistribution of 15% at the intermediate supports. Finally, I can check whether the load coefficients and combination factors are in accordance with the applied standard, and this is the case, so no changes over here. Now I want to change the height of the beam of the last span using variable cross sections. I set the height of the last span to 320. I also fill out a DH, a delta H of 70 millimeters. And this is to keep the bottom of the beam continuous, as you can see over here in the representation of geometry and loads. Notice also the jump in the reinforcement diagram. Now we have seen that with every change of one of the analysis parameters, ConCrete will perform an automatic recalculation. This is a setting and therefore can be changed. If you need to adjust a lot of data, it is useful to disable this. Afterwards, you can launch the analysis with the calculator. Finally, we will make a concise calculation note of the second beam. ConCrete automatically generates the calculation report. We just have to decide what to include. So I include the front page, the structure and loads, the reinforcement sketch, and the diagrams. And the report is ready to print. So this is the title page, the geometry and the loads, the reinforcement sketch, and the diagrams. I now also wish to add a third element, a plate bearing in one direction. The thickness is 240 mm. There are two spans of 4.5 and 7.3 meter. The loads are 3.5 and 2 kN per square meter. The settings of the active selected beam will be used as a template for the interactive questions procedure of the new element. Knowing this, I will make the first beam element active again because the plate has no height difference, and otherwise I will get questions regarding a possible height difference. Now, the plate can be easily recognized by the icon of a plate. Again, this element was very quickly introduced in the software. In this project, we only have 3 elements. But what about several hundred beams and plates in a project, like in this file? Such an amount of elements requires organization. With the project list on the left side, you can manage all beams and plates that are created in the project in an organized manner with a tree structure. Elements can be organized in classes. For example, a logical layout for all elements in a project is per floor or per block. And we can modify the names of the different classes. I've renamed some of the classes to floor +1, floor 0, and floor -1. Now we can move the slab to another class by dragging the element to the desired class. I make sure that the slab is not the active selected element. So for example, I make beam to the active element. I select plate 1 and drag it to floor -1. These 3 examples have clearly demonstrated you productively can calculate and organize continuous concrete beams and slabs with the ConCrete software.